Hello all, welcome back to Organic Chemistry. We started yesterday looking at our first note, 3.1 and 3.2 note for organic chemistry, and we looked at what is organic chemistry, and the textbook gives us a definition that I'm not sure I really like, but it's the one that we're going to go with, and it basically says that organic compounds, organic chemicals, are those that contain carbon atoms that are usually bonded to other carbon atoms, so carbon bonded to carbon, and that they usually contain other elements, principally hydrogen. So we're going to see today, we're going to talk about a group of molecules called hydrocarbons, and those are specifically compounds that contain only hydrogen and carbon. We're going to move on to look at other elements too, but we're going to start there. Now, I left you with this homework here yesterday, and I want to take just a minute and take up these questions on page 96 of our textbook. So I've downloaded this into Notability, so the questions are here. So question number 1, so here's the review. It's in our textbook on page 96 for this first topic, and I really like these reviews. I find that in a nutshell, they give you the whole synopsis, the summary of all the key points of what we've just finished. So I look at what the summary tells me. It says organic compounds are the definition I just said, contain carbon atoms, usually bonded to other carbon atoms, and to hydrogen and to other elements. And then carbon has 4 valence electrons, so it can form up to 4 covalent bonds, and also form double bonds and triple bonds, like we said yesterday, by sharing more than one pair. Remember, every covalent bond is a pair of shared electrons. It's 2 electrons, one contributed by each nonmetal atom. And it says carbon can form a variety of structures. We didn't get into that. It says Lewis structures can be drawn. We drew Lewis structures yesterday. And it says a single bond is usually drawn as a solid line or dash, a double bond as 2 solid parallel lines, and a triple bond as 3 solid parallel lines. So if I go down to the review questions, so question number 2 here is asking what is organic chemistry? So we've just gone through that. Question 3 is saying, would you define these as organic or not organic? In other words, inorganic. A is definitely organic. It's got carbon bonded to hydrogens. B is inorganic, right? It's got no carbon, so it's not going to be organic right from the get-go. C contains carbon bonded to other carbons and hydrogens. It is organic. D is a rock, so it's probably not carbon containing. Again, remember the traditional definition was if it is made from living things and or in living things, whether it's either made by them or part of them, it's usually how we used to consider things organic. So this tree here would be organic, where the rock would be inorganic. All right, so organic, inorganic, organic, inorganic, organic, right, based upon the definition that we're using for organic chemistry. Number 4 asks you, how many electrons does an atom of carbon have? We know that carbon has 6 electrons. It says, how many additional electrons does carbon need to fill its outer shell? It needs 4 more. So remember, carbon is 6 on the periodic table, so it's got 6 electrons. 1, 2, 3. So pull this down a bit. 3, 4, 5, and 6. So there's carbon. So it's got 6 electrons, 4 of them in the outer shell, so it needs 4 more electrons. Okay, how many additional electrons does it need? It needs 4 more. It says, describe how electrons are shared between carbon atoms if they have a single covalent bond. So if I've got a carbon atom with its 4 electrons, there's my Lewis diagram for carbon with the 4 dots, and then carbon is bonded to another carbon with its 1, 2, 3, and then the second pair of dots goes in the middle here, so both carbons are contributing an electron to this pair in the middle here, and then ultimately we're going to replace that pair. We're going to replace that pair with a dash, right? The dash represents a pair of shared electrons. It says, describe how electrons are shared if they have a double covalent bond. Then these 2 carbons will take a second electron each, let's say these 2, and then shift them up so that they're in the middle here. There's 1 and 2. My stylus doesn't like doing dots. So there's 2 electrons in there. So these 2 from the bottom here have been moved up, so they're now between the carbon atoms, and they can form that second bond between the carbons, and I'll end up with a double bond, which is B. And then if carbons take a third electron each and decide to share them, move them from up here down between the carbon atoms so that they can share the pair, I can now get rid of these 2 electrons up here and move them between the carbons as a pair of electrons, which becomes a third line or a third dash or a third covalent bond, and that becomes a triple covalent bond. Notice for this last scenario, the carbons have only 1 electron left, so they can still bond with another atom. Each of them can bond with another atom, right? And it might be a hydrogen, it might be another carbon, right? So again, we're going to look at examples of these in today's note. Question 6 says, an organic compound is made up of molecules that contain carbons linked by a double bond. All other atoms are hydrogens. 2 carbon atoms are linked by a double bond. Draw a Lewis diagram for carbon. Draw the Lewis diagram for hydrogen. How many hydrogens atoms are in each molecule of the compound? So let's start with my 2 carbon atoms. There's a carbon atom, and there's a carbon atom, and it says they have a double bond between them. Okay, so there's my 2 carbons linked by a double bond. Notice that each hydrogen has 2 more electrons. This carbon on this side is using 2 of its electrons in here, so it's got 2 left over. This carbon is using 2 of its electrons in here, so it has 2 left over. Now, typically, if we were doing Lewis diagrams, our 4 electrons go around the atom at 3, 6, 9, and 12, right, in the 4 corners around the carbon atom. But typically, as we're going to see in this unit, often when it's drawn with a double bond, we don't draw them quite like that. We draw them so that ultimately this is a group of electrons, right? They're negatively charged. This is an electron, which is negatively charged. This is an electron that's negatively charged. And what do we know about charges that are the same? They will repel each other. So right now, these 2 electrons on this side, these 2 here, they're pretty close, and this one is pretty close to this one, and this one's quite far from this one. So what's going to happen is these are going to rearrange themselves so that they're as far apart as they can possibly be. So these 2 electrons over here are going to move so that they are here. Oops, get my stylus going. Here and here, so that they're as far apart from the electrons in the middle here, and they're as far apart from each other as they can possibly be, and I end up just like a triangle with the points being as far apart as possible. And the same on this side. This carbon is going to take its remaining 2 electrons and it's going to put them out like this. And it says all other atoms in each molecule are hydrogens. So this carbon on this side is going to share its electron up here with hydrogen and its electron down here with hydrogen. And when it does that, I end up with this. And I end up with this. But then again, remember, instead of having the 2 dots here, we replace them with a dash. So I'm going to get rid of the 2 dots, and I'm just going to replace them with a single covalent bond. Get rid of these 2 electrons down here and replace them with a single covalent bond. The same thing will happen on this side, and the same thing will happen on this side, where I've got a single bond between carbon and hydrogen. So there's the molecule that we're looking for right now. That's the Lewis diagram, because remember, we take every pair of electrons that is a shared pair and we replace them with lines or dashes. Right? And it says, is this compound organic? It says, why is it organic? Because I have carbons bonded to carbons and additionally some hydrogens. And then question 7 says, many grocery stores sell foods that are labeled organic. Does that mean that this means they've been produced without synthetic fertilizers, pesticides, hormones, antibiotics, synthetic additives, genetically modified ingredients, or irradiation? How does this word differ from what chemists use? They're 2 totally different things. right? They're two totally different things. This is specifically talking about a group of molecules that are based upon carbon with hydrogen. This is talking about a way of farming, right? Two totally different things. It says, what else have you learned about the word organic, and how is it meaning different? How is its meaning different from how a chemist might use it? Again, so the chemists are talking about this class of molecules, where farmers, again, are just talking about a way of growing their crops. Okay, so let's move on. I wanted to take some time in this unit, take some time as we're moving through this unit and take up the homework, maybe more so than in the past, because I think it's really important for us to be doing as much practice with organic as possible, because remember, let's go right to the top here, most important thing, right? 90% of chemists are working in organic chemistry, right? This is where the jobs are. So again, I want to make sure that you're getting a good foundation, a good idea of what's involved with organic chemistry. So this next note, 3.3, I'm not going to get to 3.4 today. 3.3 is looking at a group of molecules called hydrocarbons. Hydrocarbons. They contain hydrogen and carbon only. And basically, most of the hydrocarbons that we're going to talk about throughout this entire unit are a group of hydrocarbons that are called aliphatic compounds. And again, that's not a word that I'm probably going to use again more than a couple of times in the next 2 weeks. But the other group are a group called aromatic compounds. Aromatic means they have an aroma or a smell. Smell can be a good thing or smell can be a bad thing. And we're going to see that some aromatic compounds smell really nice, and some aromatic compounds are maybe not smelling so nice, like really gross. Okay, so I want to move down and look at these compounds. We'll talk more about those aromatic compounds later on in the unit, but for now, I want to specifically look at what are some of the hydrocarbons. So when we're talking about organic compounds, if I call and order an organic compound from my chemical supplier for labs that we're doing at Bernie Custis, they'll say, what are you ordering? I'll say, I want to order some octane. I talked about octane yesterday. Octane is 8. That means there's 8 carbons in octane. And this molecule here is called pentane. Remember, 5 carbons. Remember, mono, di, tri, tetra, penta means 5. Hexa is 6. Hepta is 7. Octa is 8. Right, so those are our prefixes that we've been using in chemistry in the past, and we'll continue to use those prefixes. Now, if I can maybe just take a minute here and go back to, I don't know if I've got it still open, my periodic table. On the periodic table that I handed out to you, and I hope you've still got it, and I hope it's handy because you really are going to be using it quite often in this course. Now, if we look at, get rid of that. These laptops are quite slow. Okay, so I am going to look at, let's close up Unit 2 here. Sorry, it's taking a moment. Mr. Sinna's notes plus, and there's the periodic table right there. It's the first thing right at the top of the list. Second thing. And when we look at the periodic table that I made for us for this course, again, you know how I've already talked to you about the things that I've added to our periodic table that aren't typically on a regular periodic table. So with this periodic table that we've got on the hub here, you'll see that up here are all the polyatomic ions. There's our formula for percent yield. These are all the formulas for the math that we did in our last chapter. You may just want to be forgetting about that for now if it didn't go so well. And then I want to just scroll down to the back, or this page 2 of our periodic table, and you can see here that anytime I use the prefix for 1, it's mono, for 2, it's di, for 3, it's tri. When we're talking about organic compounds, the first four don't really add up, but then once I get to 5, I've got pentane, which is 5 carbons, hexane, which is 6 carbons, heptane, which is 7, octane is 8, nonane is 9, decane is 10. Right, so the names for our organic compounds, the basic names, notice that they all end with A-N-E, which is ane, and that's an important part of our name. And then the other important part of the name is the prefix, which tells me how many carbons are in the molecule. Okay, so let's go back to our note here. So if I'm trying to name a compound, really there's a couple of parts to the name. Okay, so I'm going to have to build the name. So if I tell you that the compound is C5H12, it turns out that there's a whole bunch of molecules that are C5H12 that are all different. And each one has different properties. And just like I might say that these 5 things are birds, you say, yeah, but what kind of birds are they? I'll say, well, that one's a parrot, and that one's a hummingbird, and that one's a robin, and that one's a black crow, and that one is a hawk. Right? Say, yeah, okay, so they're all really different, right? I say, yeah, they are. They're all birds, right? Just like if I said C5H12, I could draw out a whole bunch of different molecules that have 5 carbons and 12 hydrogens, and they would all be different. Just as different as the hummingbird is from the crow, or the hawk is from the parrot, right? These compounds themselves are going to be very different also. So I need to specifically identify which compound it is I'm using, and the way we do that is by using the name of the compound. Whoops. So when we name our compounds, we actually have to build the name. So the name itself has 2 parts. Okay, the first part is the prefix, and it indicates how many carbon atoms are in the molecule. It says you're going to need to memorize the first 10. Well, I've actually given you the first 10 on the periodic table. The second part is how that name ends. Remember I just said pentane, hexane, heptane, octane, all ending with ane. Right? What that's telling me about the molecule is that there are only single bonds between carbons and carbons. No carbon-carbon double bonds, no carbon-carbon triple bonds. Because if there was at least one double bond, the ending would now change to -ene. So instead of being pentane, it would be pentene. And that would tell me that there's a double bond, there's a carbon-carbon double bond somewhere in that molecule. In fact, there could be more than one. And if there's more than one, I need to tell you that it's diene, that there's more than one double bond. And the same thing for triple bonds. If the naming ends with "-ine", with a Y, like pentyne, that's telling me that penta, there's 5 carbons. "-ine" tells me that there's at least one carbon-carbon triple bond in that molecule. So for now, I'm going to specifically look at the alkanes. So if I look at the alkanes, this is the list that we have on our periodic table, the one that I just showed you a moment ago. And here's my 1 carbon, 2 carbons, 3 carbons, 4 carbons, up to 10 carbons. Now, when we're looking at the molecule, really, I don't typically count the number of hydrogens very often. I mostly look at the number of carbons because that tells me right off the top what the name prefix is going to be. Now, the first 4 are different than the ones that we have used previously, right? Previously, we used mono, di, tri, and tetra, right? And now we're going to actually use, I didn't mean to erase that. Now we're actually going to use penta, hexa, hepta, octa, nona, and deca, just like we have historically for 5, 6, 7, 8, 9, and 10. But the first 4 are new. And they're probably the most common ones, so you're going to get used to them pretty fast. But the first one is called methane. Methane is a molecule that has 1 carbon. Whoops. It has 1 carbon, and it's sharing all 4 of its electrons with hydrogens. So this molecule here is methane. And it's a very common hydrocarbon. It's probably, we learned about it in our ISU. Remember, it's one of those global warming gases, right? It's produced in agriculture by a lot of agriculture animals like cows and pigs and things, right? That's what makes farms smell the way they do for the most part. A lot of it is the molecule methane. Then we have ethane, which has 2 carbons. 2 carbons means carbon is sharing a bond with another carbon, and then all of the other atoms that are in there, the other 6 are all hydrogens. So I've got 1, 2, 3, 4, 5, 6, so that this carbon here has 4 bonds, this carbon here has 4 bonds. These 2 carbons are sharing 1 pair of electrons, and then the hard carbons are going to share their other 3 electrons each with 3 hydrogens. So I end up with this molecule, which is now called ethane. So the first one was methane, the second one is ethane. So there's methane up there, and here's ethane here, and it's got 2 carbons, and all the rest of the atoms are hydrogen atoms. If I move down, propane and butane and pentane, oh, space to work here, I don't. I'm going to go to my whiteboard and just clear the whiteboard here. So if I go to propane, propane has 3 carbons. It's C3H8, C3H8, and it's got 1 carbon coupled to a second carbon coupled to a third carbon. And there are single bonds because it ends with ane, propane, and C3H8. So again, notice that around each carbon I have to have 4 bonds. So this carbon at the end, the first carbon here has got its 4 bonds. The carbon in the middle has its 4 bonds. Carbon at the end has its 4 bonds. This carbon in the middle is sharing 2 of its electrons with carbons. So it's still got 2 more electrons left over that it can use. Let me erase this thing up here. So it's got 2 more electrons, so it's going to use 1 for hydrogen and 1 for hydrogen. So it's got all 4 of its electrons used. The carbon atom on the left here is using 1 electron to bond to carbon, so it's got 3 left over that it's going to bond to hydrogens. And the one on the right here is using an electron to bond to carbon, and then it's got 3 more electrons that it's going to use to couple to hydrogen. This molecule here is called propane, right? And it's basically the gas that we do a lot of our cooking with and heating with, and it's a very common hydrocarbon gas fuel. Our next hydrocarbon is C4H10. This molecule is called butane. Right, so if I go back to my note here, right, C4H10 here is butane, right? And then the next one is pentane, C5H12. So again, let's go back to my note. Oops, back to my whiteboard here. I'm going to do C4H10, so there's 1 carbon bonded to a second, bonded to a third, bonded to a 4th carbon. There's C4. And then each carbon is bonded to the remaining electrons are used to bond to hydrogen. You think, why hydrogen? Because they are hydrocarbons. Right? So if this is telling me it's butane, butane means 4 carbons. Ane says that there's only single bonds between carbons. It means if I look at each carbon, this carbon is using 2 electrons on each side, and it's got 2 left over for hydrogens. This carbon is using 2 electrons, 1 on each side, to bond to the chain, and 2 to bond to hydrogens. So I'm going to stick my hydrogens on those 2 carbons. And then the end carbon, this carbon here is already using 1 electron to connect to the chain. It's got 3 left over. This carbon is using 1 to attach to the chain. It's got 3 left over. So again, I'm just going to flood those bonds with hydrogen atoms. And if I add them up, I've got 4 hydrogens along the top, 4 hydrogens along the bottom. That's 8, 9, and 10. C4H10, and that is butane. Butane is what we use in lighters, for barbecue lighters, or for lighters that people use who are smokers or need lighters for lighting fires or lighting candles. Right. So there's butane there. The next one we said was pentane. Pentane has 5 carbons. Notice that the hydrogens are not in the middle. You think, why wouldn't I have, if I've got C5H12, Why can't I have carbon bonded to hydrogen, bonded to carbon, bonded to carbon, bonded to carbon, bonded to carbon? And there's my 5 carbons. But notice the problem here is that hydrogen, hydrogen only has 1 electron. So it can only bond to one thing. It can't bond to 2 carbons. It's impossible to have that hydrogen in the middle of a chain because it doesn't have 2 electrons that it can use to add itself to the middle of the chain. So we're going to have to get those out of there and put my 5 carbon chain together now for C5, and then put my bonds in all the way along top and bottom for all the hydrogens. And this now becomes pentane. Penta means 5 carbons in a chain. Again, notice that all the carbons inside the chain have got 2 hydrogens, and that the carbons on each end actually have 3 hydrogens. So again, if I was to count them all up, I see 5 carbons is pentane, 5 carbons, with ane, no double bonds, no carbon-carbon double bonds, and the 12 hydrogens are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the 2 on the ends make 11 and 12. Okay, so that's pentane. Okay, I can just keep going now, and the next one is hexane. It's C6H14. Again, you just need to remember hexane means 6 carbons, right? And single bonds only. 1, 2, 3, 4, 5, 6, and you put all your hydrogens in, right, all the way along here, and you end up with this molecule hexane. You think, wow, this is starting to get monotonous. Carbons and hydrogens, carbons and hydrogens. What day is it today? It's Friday. I'd say by Tuesday next week, you're going to be seeing carbons and hydrogens in your dreams. Okay, so that's this is organic chemistry, and it's all about hydrocarbons. So we're going to spend the next 3 weeks talking about these molecules that have got chains of carbons connected to hydrogen atoms that are part of the hydrocarbons. So that's C6. Then we've got C7, C8, C9, C10. Notice that for all these molecules, the carbons are in a linear chain. Right? There's no carbon that's outside the chain. It's just one long straight chain of carbons. One long straight chain of carbons all the way up to C10, which is decane. So I won't do C7, 8, or 9. Let's just finish with C10, H22. And again, this one becomes really 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you're going to flood all of your carbon atoms with hydrogens. And you get the idea. Right? So that's decane. Right? And again, I could put all the hydrogens in. I'm not going to do that. It's too hard with this stylus. It just makes a mess. But those are your basic hydrocarbons. So back on the periodic table again. Back on our periodic table, you'll see that I have for you methane, carbon 1, carbon 2, carbon 3. So it says 1, 2, 3, 4 up to 10, and this is methane up to decane for C1, C2, C3, C4, C5, pentane, C7, heptane, C9, nonane, C10, 10 carbons, decane. All right, so you've got that to fall back on. Again, keep that periodic table handy. All right, it is just it is absolutely the most vital part of what we do in chemistry, just over and over and over again. So those are all my alkanes, right? Methane up to decane. Now it turns out that, let's go back to my note. Oops. So it says draw the structural formula for propane and write its formula. So propane is going to be C3H8. It tells me up here. And if I had to draw it, I would draw it very quickly as 3 carbons. Let's just make this bigger. 1, 2, 3 carbons. And then I would put my 4, 5, 6, 7, 8 hydrogens all around. There's propane. Right, and it's done. Now, we can make this a little bit easier. Once you've been doing this for a while, you think, I'm getting tired of this. What we can do is treat each carbon atom as a structure unto itself with its hydrogens. So this first carbon here has got 3 hydrogens connected to it, so I can actually write it as CH3. This carbon has 3 hydrogens. And it's also bonded to the next carbon, which has 2 hydrogens. So the next carbon has 2 hydrogens, and then the last carbon here has 3 more hydrogens. And that's another way to write the formula for propane. So rather than having to write all the H's around with all the dashes as separate things, we can write it this way. Notice that the carbons that are in the middle of a chain typically have 2 hydrogens, right? Oops. This carbon here has its 2 hydrogens, and then the carbons that are on the end have 3 hydrogens. So CH2 in the middle, and then CH3 on the end, because the end carbons have 3 hydrogens. The end carbon has 3 hydrogens, right? So if I was doing hexane, and I wanted to write the molecule for hexane. Actually, I think it asks me to do some here in a minute. Let's see. Repeat the above for butane, octane, methane. Okay, so if I'm going to do butane, butane has 4 carbons, so I'm going to do 1, I'm going to leave some space, 2, leave some space, 3, leave some space, and 4. And the reason why I've left space is I'm going to put the hydrogens on here that would surround that carbon. So the end carbon on this side has 3 hydrogens, the end carbon on this side has 3 hydrogens, and the carbons in the middle have 2 hydrogens. Right? They have this in the middle. They only have 2 hydrogens because they're using 2 of their other electrons to be bonded inside the chain. So that molecule is butane. If I'm drawing methane, it's carbon with 1, 2, 3, 4 electrons that go all around it, and methane is CH4. It has 4 hydrogens bonded to the central carbon atom. Okay, that's the only time I have 4 hydrogens on a carbon is when there are no carbons bonded to carbon. It's using all 4 of its electrons to bond to hydrogen atoms. Okay, so there's methane, and octane again would just be CH3, CH2, 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 CH3. Right, so nice and easy for drawing these things. Now, if I scroll down here, it talks about naming branched chain alkanes, which means that the alkane, the carbon chain, isn't a straight chain, but there could be some branches on it. And the branches need to tell us how many carbons are in the branch. So just like I know how many carbons are in propane, 3, how many carbons are in methane, 1, if the branch has 1 carbon in the chain, right, if it's a CH3 part that's added to the chain, then it's going to be called methyl. If it's got 2 carbons, it's going to be called ethyl. Well, that's good because 2 carbons is ethane. If it's got 3 carbons, it's called propyl. Well, that's good because 3 carbons is called propane. So we change the ending to YL to show that it's a branch. It's off the main part of the molecule. Butyl for 4, just like we have butane with 4 carbons. So excuse me. So I will look at a few examples here. It says when we're naming these things, the easiest way for me to do this is to just do 3 or 4 examples and show you. So when I'm naming these things, I want to, number 1, look for the longest chain, right? The longest continuous carbon chain, and I'm going to name it, right? So look for your longest chain, and then name that. And then once you've named it, look for the side chains and identify what are the side chains and where are they. Okay, so let's look at a couple of examples here. So in our textbook, if I got my textbook, oops, loaded up here or not. Notability, textbook. Okay, so there's methane, ethane, propane, butane. Again, if you get stuck at all when we're doing this work, you can always go back to the textbook. It basically is doing what I'm doing, except I'm trying to explain it to you rather than you just having to read it and figure it out on your own. So you can see this bottom picture right here, just like these ones up here are straight chains, carbon, 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 right? They're all the carbons are in a chain. This one here has a straight chain, and then off the chain, there's a branch. Okay, so there's a carbon that's coming off the main chain. So what I'm going to do is I'm going to name the main chain, which has 1, 2, 3, 4 carbons. So this becomes my main part of the molecule. That's called butane. Okay, so I've named that. Just ignore this for now, right? So there's butane, 4 carbons, and now I want to say what's on that butane. There's a methyl group. There's a 1 carbon group attached to butane, so I'm going to name it. It becomes methyl butane. The methyl becomes part of the word. It's all one word, methyl butane. And I need to say where is the methyl group located on the parent chain. So there's my parent chain, there's the butane, and notice that the methyl group is on the second carbon of butane. There's 1, 2, 3, 4 carbons of butane, and it's actually connected to the second carbon. So I'm going to tell the person who's buying this chemical that it's called 2-methyl-butane. What does that mean? It means there's a butane, 4 carbons, in a straight chain. Ane means only single bond carbon-carbon bonds. But tells me there are 4 carbons, and this says that there's a methyl group added to the 2 carbon on the butane. Now notice that the methyl group is CH3. I thought methane was 4 carbons. Notice that the meth means 1 carbon, right? The 1 carbon up here is got 1, 2, 3 hydrogens, and carbon is using its 4th electron, to bind to the main part of to bond to the main chain, right? The parent chain, right? So when we're done here, I know exactly what this molecule is going to look like. Now, names of alkane, so there's methane to decane. There's the branches. So again, 1 carbon is meth, 2 carbons is eth, 3 carbons is prop, 4 carbons is but, and then they end with YL, methyl ethyl propyl butyl. You think, well, I thought if it was an end carbon, it had 3 hydrogens, but again, notice that side group there has a CH3 on the end, and then the carbon that's attached to it is CH2 because this carbon has 2 hydrogens, and then its other electron on the left here is going to be bonded to the chain. So it needs to use one of its electrons to bond itself to the parent chain, so it's going to be CH2, CH3, and that becomes ethyl. So those are alkyl side groups, just like these are alkanes. These are alkyl side groups, and they're attached to the parent chain. So if I wanted to name this molecule here, I'm going to look for the longest continuous chain, which is 1, 2, 3, 4, 5 carbons long. So it's going to be called pentane. Right, so I have named that. Right? I've named my 5 carbon parent chain, and then the part is what's added to this? On the second carbon from the end, there's a 1 carbon group, a methyl group on the second carbon. So it's going to be 2-methylpentane. Becomes the name of that molecule there. right? So the prefix here is my side group, right? And again, you can see here 2-methylpentane. Whenever we switch from numbers to letters, we use a dash, right? So 2-methylpentane, and methylpentane is one word because it's one molecule. So let's scroll down here a little further. So it says name the following compounds. If I was going to name this compound here, I'm seeing 1, 2, 3, 4, 5, 6, 7 carbons in a chain. So 7 on my periodic table tells me that it's heptane, and there are no side chains. So this first one is just straight heptane. Right. If I look at the one on the right for B, I'm looking for my longest chain. So my longest chain is 1, 2, 3, 4, 5, 6. 6 carbons long, which is hexane. Oops. Which is hexane. And now, so I've named that part so far with the 6 carbons. Now I need to add this group here, which has 2 carbons long. Right, it's 2 carbons. 2 is ethyl, so it's going to be an ethyl hexane. Oops. Ethyl hexane, and the question is, what number of carbon is that ethyl on? Well, notice here that the carbon it's on is on the 1, 2, 3, 4th carbon from the end. Oh, but if I flip this molecule around, like if you can imagine just turning your picture upside down so it looks like this is the 1 carbon, this is the 2 carbon. Like if I just flipped it upside down, left to right, and this went up on top, and this carbon came to this side, and this carbon came to this side. Now, this is the first carbon, which would be on the left side, second carbon, third carbon. If I count from this side, it's on the 1, 2, 3, 4. So I'm going to count from the end. That makes it the lowest number. So it turns out this is 3-ethylhexane. Even though it looks like it's on the 1, 2, 3, 4th carbon from the end, it's on the 3rd carbon from this end. 1, 2, 3, it's on that 3rd carbon, so I'm going to make it 3-ethylhexane. Oops. Okay, so the first one is just straight heptane, and the second one is 3-ethylhexane. Now, you can go through in the textbook and they give you an explanation of how they name all these molecules. So if you kind of get stuck and you start thinking, I don't get this, I'm not figuring it out, you go back to the book and work yourself through the steps the way they do the solution here, right? And it's a little more detailed than what I'm doing, but I think you may just find that it's that you get enough of the detail from me. Maybe not. Okay, so there's 4 practice problems here where you have to name 1, 2, 3, and 4. And then it says you have to draw some also. So let's draw these last ones here. The first one I have to draw is hexane. So I'm going to draw CH3, CH2, that's 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. Right? Boy, this stylus just doesn't want to work sometimes. Okay, so all single bonds because it's hexane. Hex means 6, so I can see that I've got 1, 2, 3, 4, 5, 6. That molecule is hexane. Now, if I have to draw 3-methylpentane, okay, so the way that we draw these is I like to just draw the chain to begin with. So let's just draw it in here. Methylpentane. So I'm going to look at the pentane piece first because that's the main root name. That's the parent name. So it's got 5 carbons. 1, 2, 3, 4, 5. All right, so notice I've left lots of room between the carbons. That would make it a pentane because of the 5 carbons. It says on the 3 carbon, I've got a methyl group. So it doesn't matter which end I'm going to count from. I'm going to count from the left. I'm going to count 1, 2, 3. So on this carbon, I need to add a methyl group. Now, notice that this end carbon here, it should be CH3. This one here is using 2 bonds, right? This carbon here is using 2 bonds to bond to this carbon and to bond to this carbon. Notice that there's a little bit of a problem here in that this carbon is bonded to 1, 2, 3 carbons. So it only has 1 electron left, so it's going to bond to its 4th electron to another hydrogen, which makes it CH. So there's not 2 hydrogens, there's not 3 hydrogens, there's just 1 hydrogen. Right, so that carbon there is CH. This carbon here only has 2 bonds, so it needs 2 hydrogens. Come on, you. And this carbon on the end only has 1 bond, so it needs 3 more hydrogens. Remember, they all have to have 4 bonds. This carbon in the middle again, remember it's got 1, 2, 3 bonds, so it can only take 1 hydrogen because it can only have 4 bonds. This carbon has 2 bonds to carbon, so it needs 2 hydrogens. This carbon has 1 bond to carbon, so it needs 3 hydrogens. So we always count up to make sure that carbons have 4 bonds, and whatever number is missing is how many hydrogens we have to add. So there's 3-methylpentane. Okay, so I'm going to leave you with questions 5, 6, 7, and 8 there also, where you're just drawing some formulas. These don't take long. Those 8 questions will probably take you 5 minutes in total, but I'm going to stop there. Tomorrow when we come back, I'm going